Let me wait another minute and then we'll begin. All right, let me begin. So today's lecture is going to be on quantization and clustering. Now, so far, we've been looking at decomposition algorithms, essentially matrix decomposition algorithms, where we were trying to decompose a matrix into bases and their weights. And the whole idea there was that if you learn the bases properly, then the weights could be used to represent the data. Now, what does clustering have to do with matrix decompositions? So let's see. So here was our problem. You were given a collection of data X, and the problem was to find a set of bases B such that each vector here can be expressed as a weighted combination of the bases. And this decomposition ideally must be exact, but when it was inexact, we wanted the error between the two to be as small as possible. Now, why was this important? With the right set of bases over here, the weights represent the data more effectively. For example, if we were decomposing music or the spectrograms for music, if the bases we discovered ended up being notes, then these weights would basically tell us how the notes were played. So also when we are analyzing face data, if the bases give us essential facial structures, then the manner in which they are combined makes a lot of sense. And so with the right set of bases, the weights can represent the data very effectively. Also, if the bases are agreed upon, then we can communicate the information about the data more efficiently, because if you and I agree upon what bases we are using to represent the data, then I just have to send you the weights. So once you got the weights, you could combine the bases with those weights and reconstruct a pretty good facsimile to the original data. So for example, we could just transmit eigenface weights so long as you and I had agreed upon what eigenfaces to use. And then once you got the weights, you could combine your eigenfaces with those weights and reconstruct the face. Or notes are universal. Everybody knows what notes are, which means we're able to write down the score, and the score is sufficient for anyone to recreate music. So getting the right set of bases is very important. Given this, what is the most accurate way to represent data? If I want to have a representation which guarantees that I transmit the least amount of information to you, the smallest set of numbers, and at the same time, you are able to reconstruct everything very accurately, then the most accurate way to represent data is for me to have a dictionary of all possible data. If you and I had a huge catalog of every face in the world, then when I wanted to send you a picture of somebody's face, I won't send you the picture. I just say it's catalog number 763. And so once you knew that, you just pull up the face, you have the reconstruction. Now, if I want to think of this in algebraic terms, I would have a dictionary of faces these DIs are my dictionary entries, and you would be reconstructing the data as a weighted sum of dictionary entries, except the weights are going to be 0 for all of these dictionary entries except the target face. And for that target face alone, the weight would be 1. So W would be a sparse vector. It's going to have only one entry, which is 1. The rest are 0. And in fact, it's a one-hot vector because the one non-zero entry is also going to be 1. Did this make sense to you guys?
Yeah.
Yeah, right. So given this, what would be the problem with a representation of this kind? Anybody? What would be
You
the
can't possibly collect all instances of data. So for the faces, for
yeah?
example, you can't have a collection of all possible
y-
faces.
That's right. It's infeasible to construct a dictionary of every possible data instance. You would need infinite entries. Also, this is not really efficient because if I have infinite entries in my dictionary, then the index is going to need infinite bits to represent. So, this is not going to be very useful, right? And if I say that my training data is going to be finite, you would still need to store the entire training data. But then if you had to represent a face outside this training set, you're not going to be able to represent it. So that doesn't work. So can we have a solution around it? Instead of storing everything, can I instead construct a smaller finite dictionary such that all data are not now no longer exactly reconstructed as a weighted sum of the dictionary entries, but approximately reconstructed? The rest is still the same. I'm still going to reconstruct the face as a weighted sum of dictionary entries. The weights are still going to be one hot, meaning 0 for all but one entry and 1 for the one remaining entry. And what has changed is that instead of saying that this face is exactly the 7th face in the dictionary, we're going to change that to saying the face that I'm sending you looks a lot like the 7th face in the dictionary. When I send you a weight vector with a 1 in the 7th position, I'm just telling you that this face that I'm trying to convey to you is very similar, extremely similar to the 7th face in the dictionary. So what do we mean by looks a lot like or is extremely similar to? And how do we construct this dictionary such that this approximation error is minimized? So let's look at these two questions. But is the problem statement here making sense? What I just said, yes or no? What about the rest of you? Would that make sense? Okay. So for this, first, let's see what do we mean by looks a lot like? This means we're quantifying the error. And so this term is what we're trying to quantify. You're going to get some approximation. You have the original face. You want to minimize the error between the two. And you can choose different error metrics to quantify the difference between the two. Let me just generically represent this error metric as this term div, which means divergence. My reconstructed face, this one here, can be written as D times W, where D is a dictionary containing all of these faces, and W is a one hot vector. And so my way of representing one hot is the same as saying that the zero norm of W is 1, which means there's only one entry in W, which is non-zero, and that the sum of the entries of W is also 1. So these two together specify that the weight vector is all 0 except for a single entry whose value is 1. So my approximation f hat is D times W, where W satisfies these constraints. My error is going to be the divergence between the actual face and this approximation. And a very common choice of this divergence is the L2 error. Now, again, I'm speaking of faces, but this applies to any data. I'm just using faces as my example, right? So that sort of defines or quantifies what we mean by looks a lot like. The second question is, how do you construct this dictionary? Now, for this, let's say you have a collection of training data represented by this vector V. And then you have a dictionary D of k entries, which is a matrix of dictionary vectors. So this is your dictionary. Then for corresponding to each one of my training data instances, I'm going to have a weight vector, which specifies which of these dictionary entries is closest to this data entry. And so I'm going to have a matrix of weight vectors where there is one weight vector corresponding to each one of my training data instances. And so now our problem for learning this dictionary is actually the task of learning both the dictionary D and the weight matrix W to minimize the error between V and DW, subject to the constraint that each one of these weight vectors is one hot. So our optimization algorithm to learn the dictionary is given by this formula here. You're trying to minimize the divergence between V and DW. DW basically is approximating every data instance in V as a single dictionary entry. So this is minimizing the sum of the divergences between the individual faces and their approximations given by D times WI, with the additional constraint that each of the WIs is one hot. Now this is finding both the Ds and the Ws. If you're only interested in finding the dictionary, then you're going to replace the argmin with just a min over W for the individual data instances. And so now you have a mathematical formulation which we can use to estimate the dictionary. This making sense? Yes or no? Okay. And how can you do this? This is what we want to do. We want to find the dictionary such that, again, the thing about doing this, min over W summation I divergence, which means that I'm finding the set of Ws, but then I can minimize the error individually for each of the training instances. So instead of saying min over W, the sum over all training instances of the divergences for the individual training instances, I can move the min inside. And this is still the same formulation. All I'm taking advantage of is that the individual training instances are different, independent. And so finding the optimal dictionary is the same as finding the dictionary such that when I sum this term, which is to say that for each of my training data instances, I find the weight vector which minimizes the divergence. And then I find the dictionary that minimizes the overall divergence given by this formula. So did this make sense? Yeah.
Hey, Prof, I had a quick question.
Yeah.
How are you enforcing W will be one hot with this objective?
Okay, let's get to that, right? Did this equation make sense? This is a constraint optimization. I have not specified how the constraint is satisfied.
Oh, okay, got it. Yep.
Yep. By writing it in this manner, the min moved inside the summation. What this means is that now, if this allows me to do something interesting, because I'm minimizing both the Ds and the Ws, this is a non-convex problem because I'm selecting individual dictionary entries. Nonetheless, I can give you an iterative solution that is guaranteed to decrease the overall error at each step. In the first step, I can initialize the dictionary and solve this inner minimization for each training instance. And in the second step, so that's going to give me a WI for each training instance. In the second step, now I can fix the WIs and find the D that minimizes the total error. Then I can go back, I have the D, and then I can go back and minimize the error for the individual training instances to get the Ws all over again, and then use those Ws to go back and learn the D. At each step, because there's a minimization, each of these steps is minimizing the total error. And so this is a guaranteed error minimizing algorithm, which is guaranteed to get to a local minimum. Did this make sense? Right. So, okay. Now let's see how this goes. For when I use the L2 divergence, this gives us the well-known k-means algorithm. Why? If I'm going, how do you solve this first one using my constraints? My dictionary is given, correct? So how do you solve for this one? Anybody? Guru, how would you solve for this? Given the dictionary.
Just take the second derivative, equate to
Do I need
0.
to? Remember, I know that W is 1 hot, correct?
Yep.
So that's basically a selector variable. It's selecting a dictionary entry, correct?
Yes.
So all I need to do is to scroll through the dictionary entries and find the dictionary entry which is closest to VR, right? That makes sense?
Yep.
Right. And so this algorithm, this step over here is literally selecting the best dictionary entry for every training data instance. And there's going to be a corresponding weight vector, which is 1 hot. And now this tells you which dictionary entry goes with each training data instance and then, so you've got the W's and then fix the W's and optimize the T's. This one can be optimized because the W's are given, but this is not a selector algorithm. There's no constraint on D. So this can be minimized by taking the second derivative, and equating it to 0 and such like. Does this make sense? Everybody?
First, quick question here. So, won't this result in D nearly being equal to V?
Will it?
I mean, dimensionally, not necessarily, but like it feels like
If the size of the dictionary is the same as the size of the training data set, D will be V. But if
Okay.
D is smaller than the size of the training data set, will D be V?
No, it will not. It will not. Yeah, there'll be some error
Okay.
there. Yeah.
So it's no, but then what happens? For any given dictionary entry, there are going to be multiple faces that got mapped onto it, right?
Correct. Yep.
So then how do you solve for this? For that dictionary entry, you're going to find, you're just given the information. These 10 faces are mapped onto the same dictionary entry. Given that, which dictionary entry, which vector minimizes the average error over all of these guys? That's simply going to be the mean if you use the L2 divergence.
Okay, understood. Yep, thank
Right.
you.
That's why this becomes the k-means, right? So grouping VI by the dictionary entries they're assigning to WI results in clustering, right? Yes or no? Because multiple training data instances would all be mapped onto the same dictionary entry. And second, okay, before that, here's a poll. Let me release the poll. You can read it on the screen. Can you guys see the poll?
Yes.
Okay, 10 seconds. All right. So let me end the poll and share the results. And most of you thought all 4 of these are true. Let's see if you're right. Indeed so, right? K-means models a dictionary-based representation. So dictionary-based representations represent data as entries from a dictionary. The ideal dictionary includes every possible data instance. Dictionaries can be estimated by minimizing the total divergence between the original data and a one-hot dictionary-based composition of the data. So I'm assuming at this point, you can see how this actually ends up being. K-means is an instance of a matrix decomposition algorithm, right? It's a constrained matrix decomposition algorithm where the columns of W are one hot. Does that make sense? Right. So beautiful, right? I've just showed you that a very popular algorithm is just something that we've always done. So let's move on. Now we've seen, so we saw this from the algebraic perspective. But I'm going to move ahead and look at the more naive procedural perspective that all of you are very familiar with as a precursor to something else. And so we're going to look at clustering, specifically K-means clustering. Now, much of statistical modeling attempts to identify latent structure in data, structure that's not immediately apparent from the data, but which, if known, helps us explain it better and make predictions. So clustering methods attempt to extract such structure from proximity, how close things are to each other, which is first level structure as opposed to deep structure. And we're going to see other forms of latent structure discovery later in the course. So here, for example, here's this was a picture, and you can see the colors which have all been assigned as belonging to which indicate which pixels belong to the same group. So what have we done over here? We have actually clustered pixels together. In the process of clustering, we've actually managed to extract semantically meaningful groupings, right? So this is the whole point of clustering. But then how did this clustering actually get done? Now, clustering is the determination of naturally occurring grouping of data instances. What do I mean by grouping? You want low within group variability and high between group variability, meaning all the data within a cluster must be similar to one another, but across clusters, they must be far apart. And so here, the two obvious clusters for this picture are these guys, right? But then, in order to do this, we need to quantify a few things. We want to find groupings such that the groups optimize a within group variability objective function of some kind. So we need to quantify the within group variability of all of these guys. And the nature of the function affects the clusters you will get. So for example, if I were just looking at how far all of the data points within any cluster are from the mean of the cluster, then in this data, the two obvious clusters are these two guys, right? But can you identify two other ways of clustering these data? Anybody? Or can you identify another way of clustering this data into two clusters?
Inner circle and outer circle?
That's it, right? But for this, you needed a different distance measure. And the distance measure you would need over here is the distance from the center, right? So the objective function affects the nature of the clusters you discover. Now, why clustering? Automatic grouping into classes gives us information, semantic information, if you do it right. But then you can also use it for quantization, because all the data within a cluster are represented by a single point, and often clustering is used as a pre-processing step for other algorithms, like indexing, categorization, and so on. So here, if you look up clustering on the web, very often you'll end up with data from the humanities, and so if you actually go to the census board, you'd get data of this kind, and they often run well-known algorithms, PCA followed by K-means clustering. What they're really trying to do is to find natural groupings of the population. Here, for example, they ran clusters based on a representation based on age, income, and education, and they find different kinds of clusters. So this is discovering latent structure in the data. But then you can also discover semantic structure, like in this example over here. Or you can use this for quantization. For example, if all of these green dots represent your data, then clustering could say that could partition the data into these cells as seen over here. Now, each of these cells has a central vector shown by the star. And now within each cell, you can approximate every training data vector by just the central vector within the cell. And so what we have done is quantize it, because here in this example, you have, I think, I don't remember the exact number, something like 32 cells, which means that if I store these 32 red dots, then anytime I want to send you information about a data instance, I just have to say, oh, this was from cell number 17. And then you'd pull up the representative vector from cell number 17. And that's going to be your approximation to that data instance. So this is quantizing it. And so clustering can be used for quantization. This is the basis of the famous Linde-Buzot-Gray algorithm, LBG. Now, so quantization, formally, what is it? Again, remember, this is what clustering was. You're trying to do V equals WD, except this is an approximation. If you use the approximation as the representation for the data, then no matter what data point you throw in, the output, the approximation is only going to be one of these 32 red dots. So you are mapping all the data point into one of these representatives. That is quantization. What about representation? This is a famous example I used to play back when this guy was famous. This was the second guy to get 1 billion hits on YouTube, I think, Despacito. Now, if you wanted to recover all the videos on the web from these guys, how would you do it? You could build a classifier, but then that's kind of complex. The simplest way to do it is to represent this video using some kind of a vector, represent all the videos on the web using the same formalism, and find the videos which have, this, so you can get a query vector from this video and pull up all the other videos whose representative vectors are closest to this query vector. And the way you would normally do it is that, at least back in the day, and even now, a video consists of many frames. From each frame, you can get a collection of features. So eventually a video is going to become a scatter of a large number of feature vectors. And then if you had a collection of training data that you had clustered, and if you had drawn these cell boundaries, then for any given video, you could just find out how many vectors, feature vectors fell in within any cell. So, and then create a representation from it. Differently stated, for every vector that you got from this video, you would get one weight vector W, which was one hot. If you sum them all up, then you're going to get a vector where each entry tells you how many of the original data vectors fell in each cell. And this F would become a representation that you could use to perform retrieval. So again, you can do things like you can use clustering for doing things like deriving representations. So for all of this, you want the clusters to be meaningful. There are two key aspects here. One is the feature representation used to characterize the data. And the second is the clustering criterion employed. How did this frame of video become one or more feature vectors? And then how did you cluster them? Which distance metric did you use? For now, I'm going to assume that this is not something we will address because we've been talking about features all semester long. Let's look at clustering. The clustering criterion actually has two aspects. There's a cluster compactness criterion, which measures how good clusters are, how compact they are. And the second is a distance of a point from a cluster, which tells you how far any data point is from a given cluster. So here are some compactness criteria. If I have if I want to hypothesize that these data points form one cluster and these data points form one cluster, then a criteria I could use is what is the total distance between every pair of points within a cluster? So that would be the total length of all of these lines. So that's a total distance based criterion, compactness criterion. Alternately, I could have something like this. If these were my hypothesized clusters, then I could find the distance between the two farthest points in each of the cluster. And so my compactness criterion would be the sum of these two, the lengths of these two black lines. Or I could look at the total distance of every element in the cluster from the centroid of the cluster. So here, if these were my hypothesized cluster, each of the clusters would have a centroid shown by the red dot. Every data instance within a cluster is going to have some distance from the centroid. And my compactness criterion is going to be the total length or the total squared length of all of these black lines. And the distance, of course, can be computed using various distance metrics. So all of these are different objective measures for quantifying the compactness of a hypothesized cluster. The second quantification we need is to determine how far a data point is from a cluster. So again, there are different ways of doing it. You could find the distance of the data point from the centroid or the mean of the cluster. Or you could find the distance of the data point from the closest point within the cluster. Or you could find the distance of the data point from the farthest point within the cluster. Or you could compute the probability distribution of all the data points within the cluster. And then given the new data point, you could compute the probability from this estimated distribution. And then the compactness, how close any data point is to a cluster would relate to how probable that data point was on this distribution. So we've defined both. How do you define the compactness of a cluster, and how do you define the distance of a data point from a cluster? Or we can do something more crazy. We could try to fit a regression to the data points in a cluster, and then given a new data point, you could see how far it was from this regression line. These are all different ways of quantifying the distance of a data point from a cluster. So, do these things make sense? Questions? What about the rest of you? Okay. So now, when I'm finding the optimal clustering, how would I do the optimal clustering? I'm going to look at all of my data points here. And I'm going to try to hypothesize every possible way of clustering these. If I decide to have, for example, two clusters, I will hypothesize every possible way of separating the data points into two clusters. And then for each of these hypothesized clusters, I would find the compactness criterion. I'd search through all of those and find the clustering which optimize this compactness criterion, and that would be my cluster. Now, for even two clusters, if you have n data points, you have 2 raised to n possible ways of grouping the data into two clusters. More generally, if you have m data points and you want n clusters, the number of ways of separating m data points into n clusters is going to be this crazy formula over here. And so exhaustively enumerating each of these ways of clustering the data so that you can compute the compactness objective and pick the best clustering is simply not going to be feasible. Unfortunately, this is the only provably correct way of finding the optimal clustering. It's just that this is computationally unrealistic, and so we are never going to do it. We are going to use greedy algorithms. And with that statement, let me see if I can pull up the second poll. Can you guys see the poll? Okay, 15 seconds, guys. All right, let me end the poll. Anyway, so anybody want to tell me what the answer to the first question is? True or false? Yeah, there are many ways of defining it, right? What about the second question? Which of these is true? So that would be these two, right? Thank you. So you get the idea. Let me move on. So I'm going to move on to a not quite non sequitur problem, that of scalar quantization. And this has to do with how we represent data in real life. So for example, if you're capturing images, what do images capture? Those RGB, GB values you're capturing are representing the intensity of the light at 3 wavelengths. But intensity is a continuous valued variable. It can be anything between some minimum value and some maximum value that you can sense. On the other hand, you use only 8 bits to represent R or G or B. 8 bits can only represent 256 values. Intensity itself can take any value over here. So how would we map this continuous range of intensity to one of these 256 values? The simplest way to do it is to say I'm going to partition this range of possible, continuous range of possible intensity values into 256 uniform bins. In this example, I have 7 uniform bins, right? So 8 uniform bins. There was supposed to be 8, but I'm showing 7. And then you can say something like, or if I had 4 bins, I could say something like if the intensity is greater than 3.75, then the bin value is 4. If it's between 3.75 and 2.5, it's 2. If it's between 2.5 and 1.2501, so you can actually, 3, 2, 1, 0, right? And so for each bin, you would have an associated index, and all you would store was the index of the bin that the data fell into. And now, if the bin numbers are linearly related to the actual intensity values, then when on the receiving end, when you get these bins, if you want to try to reconstruct what the actual intensity was, you know that when you got 0, 0, it's way to the far left. So the intensity value is probably close to 0. So you can just say 0. When you get 0, 1, it was the next range. So the intensity value is 1 times some constant. If you got 1, 0, it was in the next range. So the intensity value was 2 times some constant. If you got to the next bin, it's the next range. So the intensity value was 3 times some constant. And so this reconstruction was simple. You just read the index value and you multiplied it by a constant to come up with an idea of how intense the light was or how much the signal value was. Now, the problem with this is that it ignores the actual distribution of the real valued data. In most real life, the real valued data would have a distribution of this kind, where some values are much more common and other values are rare. And this kind of representation is giving equal weightage to errors in the more probable regions and errors in the less probable regions. So a non-uniform quantization of this kind, where the bins in the high probability regions are smaller and the bins in the low probability regions are wider, is going to give you lesser overall error, except now, you can't just read this bit value and multiply it by a constant. You actually need a table to see what each of these must be mapped onto, because the centers of these different bins are differently spaced. And this is, in fact, is what is used in very common audio representation formats, mu law and A law, where the bins are non-uniformly spaced according to a formula. This making sense? Yes or no? Okay. So wait. All right, Verity. Where did I like why? Simply because if I have only, let's say I'm using only 2 bits to store my data, right? Then you want the average error across all of your data to be minimized, correct? Verity? And which of these would give you lower average error? So over here, what would happen is that the frequently seen values are going to have lower error. In exchange, you're going to have higher error on infrequently seen values, but because they are rare, they don't really show up very frequently. So on average, this would have lower error. Did that clarify? Verity? Okay. So here we have formula, but what if you have data whose distribution looks like this? And suppose I give you a fixed number of bits. How would you decide the width of the bins? Where would the bins be narrow and where would the bins be wide? Anyone? How would you decide the width of the bins here? Anyone? Everybody's awfully quiet. So can I pick on somebody? Let me say, you want high probability regions to have narrower bins and low probability regions to have wide bins because you know that data only falls here. There's no point in having many bins in these regions, correct? So you want to have lots of bins in these regions and very few bins in these low probability regions, right? Yes or no? So what is the problem with doing this? The problem is you would need to know the distribution. In reality, you're not going to have the distribution. You're just going to have a bunch of training data. So you have to somehow estimate the bins from the training data without knowing the actual distribution itself. And this is the Lloyd quantizer. It's an iterative algorithm for computing optimal quantization tables for non-uniformly distributed data. It's learned from training data. And the way we do it, you have a bunch of training data which have been drawn from this distribution. You never see the distribution, you just saw the training data. And then you randomly initialize the centers of the various bins, which are the, these values, right? These are the centers of the bins. And then you got a whole bunch of training data points, and you know that the boundary between 2 bins is the center, exact center. Anything to the right of the center is going to be assigned to this bin. Anything to the left is going to be assigned to this bin. So you take all of your training data and assign them to the individual bins based on which of these representative vectors, which we'll call the centroids, we are closest to. And now, when you do that, you're going to get, so here, for example, on this bin, right? This guy is going to see a lot more data from the left side than from the right. Yes? This bin. What do you think? So consider this bin. Will we be seeing a lot more data from the left than from the right or not? So is there a better representative for this bin than the center of the bin? What would a better representative be? Something that's closer to the high density values, because that's where most of the guys will come from, correct? Yes or no? Right. And so now, if you just collected all of the data that fell within each bin and found this new centroids, the centroids would have shifted. But then these centroids are now your initial centroids, and then you can draw new boundaries and repeat the process. And you can keep doing this until it converges. And eventually you're going to get a bunch of centroids which are automatically clustered in the high probability regions, and you're going to see very few of them in the low probability regions. And this is an optimal quantizer, because if you quantize data to these centroids, you will make the least quantization error. So this was a very famous algorithm by Lloyd. And the interesting thing is that this paper came out in 1982 or thereabouts. But it's actually based on k-means clustering. And the original k-means clustering paper came out in 1967. So the Lloyd quantizer is a one-dimensional instant variant of the generic k-means clustering algorithm that McQueen came up with in 1967. And it was published 15 years later. So it just goes to show that, sometimes you can get a paper by reducing the dimensionality. You don't have to make the problem more complex. Just making it less complex can get you a paper and an award-winning paper. Anyway, so here's the general k-means clustering algorithm, right? The generic procedure is you initially group the data into the required number of clusters somehow. Then after that, you go through all of your training data point and assign each data point to the closest cluster. And then once all the data points are assigned to the clusters, you're going to be redefining the clusters and you iterate. So here's how you have normally seen k-means clustering. Let's say the problem is given a set of data points shown by these colored dots. You want to find the natural clusters. And the clustering criterion we would use typically is the scatter, which is the total squared length of the distance of each data point from the centroid of its own cluster. And the centroid is generally defined as the weighted mean of the cluster, where in the simplest case, every data instance is given equal weight. So all the W's are 1. So how would this work? You initialize the set of centroids randomly. Then for each data point, find the distance of the data point from the centroid of each cluster and assign the data point to the cluster corresponding to the closest centroid. You do this for each of your data points. And now you're going to have different sets of data points assigned to the different clusters. These form new clusters. And then from these clusters, you can go ahead and re-estimate the centroids and repeat the procedure. This is how you have studied k-means clustering. So when we were doing this, going back to our algebraic representation, what were we doing? When we were finding the distance of the data point from each of the cluster centroids and picking the closest one, what were we doing? Can you map it onto the math that we saw early in the class? Akanksha, this is the number of clusters. But what is this assignment doing? Anyone?
Dictionary. It's similar to the quantization that we did.
No, but this was
earlier.
estimating the one hot weight vector. This is computing the one hot weight vector, right? You're representing this data point as a weighted sum of these dictionary entries, except the weight for only one vector is 1, dictionary entry is 1, and the rest of them have 0 weight. So you search through all of these guys and say, which of these must I give a weight of 1 to? And that's basically what's happening over here. That makes sense? Yes, no. What about the rest of you guys? Does that make sense? Okay. And so now you got your new clusters and you can iterate, right? And the distance metric determines the clusters. In the original formulation, the distance is L2. And if you replace every vector X by the centroid of its cluster, you got vector quantization. K-means is an instance of generalized EM. And it's this simple way of doing it is not guaranteed to converge for all distance metrics, but you'd have to be careful because for some divergence functions, finding a centroid such that the total divergence over all the data point within the cluster is minimized. Can be an intractable problem. But anyway, here is a poll. Let me see if I can pull this up. Can you guys? I'm trying to launch this. Wait a minute. Give me a second. The previous poll is being shared for some reason. Okay. Can you see the poll? Karan, why didn't people just call it 1D K? 1D K means. That's what it was. It was 1D K means. So the crazy thing is that this guy Lloyd came in 15 years after the original McQueen paper. So Linde, Buzo, and Gray came in 10 years after the original McQueen paper. 10? Yeah. Or 15 years, or 15 years after the original McQueen paper, and republished it and used it for quantization and called it vector quantization, and it became a big deal. Then Lloyd came even later and did 1D VQ, K-means, and called it optimal scalar quantization, and that also became a big deal. So K-means clustering is one of those algorithms where the papers traveled in the reverse direction of the complexity of the technology. So I'll stop it right here. We've had this for a minute. 5 seconds. And poem. Here it is. Okay. So what is the answer to the first question? True or false? True. What about the second question? What is the answer to the second question? Anyone? Let's see what the answer is. Like I said, if you change the formula for the distance to the center cluster was simply picking the cluster for which we had the lowest divergence. So so when we stated that, we did actually specify what the divergence formula was. The real challenge isn't going to be figuring out what the centroid is. For complicated divergence formulae, finding the representative, which minimizes the divergence over all the training data, is going to be really hard. Anyway, this kind of clustering, if you just use L2 divergence, then you're always going to be able to find clusters of the kind shown to the left. But you cannot find clusters of the kind shown to the right. This will not happen, right? So how can I go ahead and find clusters of this kind? For this, I want non-Euclidean clusters, right? Now, how can I come up with a mechanism that still uses k-means based on L2 divergence? So I don't go searching for some fancy new divergence technique, but somehow manages to group the inner circle and the outer circle into the two clusters. To do this, I'm going to retain the xy coordinates of the individual data, but then I'm going to add a z coordinate to each of the data points. The z coordinate is going to be some alpha times the squared norm of the vector, which is the distance, squared distance from the center, assuming the origin is at the center. If I do this, then instead of just being a two-dimensional plot, all of these data points end up being on a quadratic bowl because the z-axis represents the distance from the center of the circle, right? And so this z-axis, for small alpha, the inner and outer circle data points are going to be close together. But as you keep increasing alpha along z, the distance between these two clusters is going to keep increasing. Do you see this? Over here? Right. What about the rest of you guys? You see that? Yeah. So all I'm going to do is convert this two-dimensional data into three-dimensional data by adding this new z. And then now I can just run standard k-means. And magically, the two circles are going to get grouped into two different clusters. So this is what is called kernel k-means. You're putting the data through a kernel function, which converts it to a higher dimensional space, and then you do your clustering over there. There are other related clustering algorithms like spectral clustering, normalized cuts, but all of them relate to this technique. So just understanding this method is good enough, right? So this would mean that the centroid for each of the concentric data would fall, in this case, along the z-axis, or the centroid is going to have an x, y, and z component. That's what it means, right? The xy components are going to be close to the origin. The z component is going to be something non-zero. Did that answer your question, Abhishek? Right. So anyway, so what we are doing here is transforming the data into a synthetic higher dimensional space where the desired pattern becomes natural clusters based on Euclidean distance. Here, I knew what to do. You know, the z-axis had to be some alpha times x squared plus y squared. More generally, what is the space? There's also this problem, converting this data into a higher dimensional space and computing the Euclidean distance there can be very expensive. And yet, this going into the higher dimensional space and computing the distance didn't actually introduce any fancy new information besides what was there in the lower dimensional space. Now, so how do we deal with this? So for this, first, let's see what we are doing. We are transforming our data through a possibly unknown function phi so that you go into a higher dimensional space. Here, for example, we went from 2 dimensions to 3. Then we are performing Euclidean clustering in the higher dimensional space. The distance between two data points in this higher dimensional space is simply defined as this squared Euclidean distance between the z's, which are phi of x, which is the squared Euclidean distance between phi of x1 and phi of x2, where phi of x is the transformation into the higher dimensional space. Now look at this. This distance in the higher dimensional space, which is this guy, do I need to explicitly compute phi for this? Or can I just treat it and view it as some function of x1 and x2 in the lower dimensional space? What do you think? Look at this. I don't really need to go into the higher dimensional space. I should be able to compute d without computing phi. In fact, I don't even need to know what phi is. So this means that I can hypothesize distance functions in a higher dimensional space without knowing what the higher dimensional space is. How do I do this? To do this, I need to know the nature of functions functions dx1, x2 that guarantees me that this function is actually computing a distance in a higher dimensional space. Now, to see what kind of function that should be, let's look at what the distance in the higher dimensional space is. That is z1 minus z2 squared norm, which is to say z1 minus z2 transpose z1 minus z2. If I expand it out, it's going to be z1 dot z1 plus z2 dot z2 minus 2 times z1 dot z2. But then z was just phi x1, z2 was just phi x2, right? So this is phi x1 times phi x1 plus phi x2 times phi x2 minus 2 times phi x1 phi x2, right? This making sense? This function? So what about the rest of you guys? So what this is telling me is that if I could somehow compute this inner product, phi x1, phi x2, without actually computing phi, then I can compute the distance, correct? All I need to be able to do is to compute this inner product, and then I can compute the distance, right? Yes or no? Okay. And so that is what about the rest of you? Is that making sense? I got 3 S's. Again, if I could somehow compute phi x1 dot phi x2 without computing phi, then I can compute phi x1 dot phi x1 using the same approach, phi x2 dot phi x2 using the same approach, and this guy. So I can compute this entire term without ever computing phi, and so I can compute the distance. And so I can do my clustering, right? For this, we introduce the kernel function. A kernel function is a function such that kx1, x2 gives me an inner product in some higher dimensional space. I don't need to know what are the higher dimensional spaces. I'm just telling you, here is a function. I'm giving you a guarantee that this is computing an inner product in some higher dimensional space. So what kind of function satisfies this property? We will see. But assuming that I had a kernel function of this kind, then the distance between 2 points x1 and x2 in the high dimensional space is simply phi x1 plus phi x2 minus 2 times phi x1 phi x2, which is simply the kernel computed between x1 and itself, plus the kernel computed between x2 and itself, minus 2 times the kernel computed between x1 and x2. Is this making sense? Okay, what about the rest of you guys? 5 yeses. Okay. For this, I need to know what kx, what kind of function k computes an inner product in higher dimensional space. And for that, let's look at a very special property of vectors. For any vector v, the inner product of the v with itself is simply the squared norm. And we know that the squared norm of a vector is always non-negative. If it's a 0 vector, it's 0, otherwise it's a positive number. If I take any vector u, which is any linear combination of a bunch of vectors, then the squared norm of u is also guaranteed to be non-negative, right? Is this statement making sense to you guys? The one in black? So, but then I can replace u by this weighted sum of the vectors, which means that summation I, ai, vi transpose, summation I, ai, vi must be greater than or equal to 0. Expanding it out, it means that, you know, the sum over I and the sum over j, the product of ai, aj, vi, vj, which is what this term is always non-negative. This is just simple linear arithmetic manipulation. Is this making sense? And this should hold regardless of A. This should hold for every real AI and every real AJ, correct? So this should also hold in the higher dimensional space. No, VI and VJ, we're not making any, it can be any VI, right? We know that regardless of the nature of VI, its squared norm is non-negative, correct, Abhishek? For
Yep,
any vector
correct.
V.
Yeah. Yeah.
So this is generic. There's no constraint, right?
Okay. Okay.
So in the higher dimensional space, this must hold. Summation ij, ai, aj, zi dot zj should be non-negative. In other words, summation over ij, ai, aj, phi x1, phi xi, phi xj, this inner product must be non-negative. So we get this lovely property. Any function kx1, x2, which has this property, summation I, summation j, ai, aj, kxi, xj is greater than or equal to 0. If this property holds, then it means that this function k is actually an inner product in higher dimensional space. Relate this guy to this equation, and you can see how the k over here is the same as this term here. This making sense? Just by visual inspection. And so any prop function k which satisfies this property is guaranteed to be a function that is somehow computing an inner product in some high dimensional space where we may not even know what that space is. So this condition is called Mercer's condition. As a corollary, if any function k satisfies the Mercer condition, the distance between any two data points in that high dimensional space has this property as kx1 x1 plus kx2 x2 minus 2 kx1 x2. And because it's a distance, it satisfies all the usual properties of distance. The distance of any x with itself in that high dimensional space is 0. The distance of any x between any x and any y in that high dimensional space is going to be non-negative. And in that high dimensional space, dxw plus dwy is greater than or equal to dxy. This is the triangular inequality. These must hold, simply because this is an actual Euclidean distance in the high dimensional space. Did this make sense? Right. So these are just properties of Euclidean distances. Anyway, what kinds of functions are kernels? Turns out there are quite a few. There's the linear kernel, which is just the inner product between x and y plus c. There's the polynomial, which has this form. There's a Gaussian. In fact, the Gaussian kernel has a very interesting property. It actually computes the inner product between two vectors in an infinite dimensional space. That's amazing, right? And you manage to compute it without actually going into the infinite dimensional space. And for the longest time, coming up with better and better kernel functions was a cottage industry. Anyway, once we choose the kernel function, in this case, the kernel function was x transpose y plus c squared. So the polynomial kernel, quadratic kernel. So let's see how we can perform the k-means algorithm in this high dimensional space, the space of phi x. Here's the algorithm. There's one problem. If you're using kernel functions, you don't actually know what the high dimensional space is. So you don't work in the high dimensional space. You're always working in the low dimensional space, and you're computing distances using this formula, which is computed directly of the kernels. So you never actually compute phi of x, which means that you cannot compute the centroid of a cluster, because the centroid of a cluster must be computed in the high dimensional space. So this computation is going to not be feasible because we don't know what phi is. And so even if you want to perform a weighted average, you can't do it. So we may never actually be able to compute this mean because phi of x is not known. So here's how we're going to perform k-means in this high dimensional space. We're going to initialize the clusters. In standard k-means, you initialize the centroids of the cluster. Here you initialize the cluster. You say these data points belong in one cluster and those belong in another cluster. Then you go back through each of the data points and you find the closest cluster, which is to say you find the cluster such that the distance of the data point from the centroid of the cluster as computed in the high dimensional space is minimum. So this has to be computed in the high dimensional space without explicitly computing the centroid in the high dimensional space. As it happens, if you work through the arithmetic, it turns out that this distance, computing the distance of a vector from the centroid of a cluster in the high dimensional space, can be done entirely using kernels, using the formula here. I'm not going to explain the formula. You can just check it up on the slide and you can implement it. But the point is it can be done. And then once you do this, here's how kernel k-means will be done. You initialize the set of clusters randomly, except now you're initializing the clusters, not the centroids. The centroids are virtual. We don't actually compute them explicitly because you're working you want the centroids in the high dimensional space, right? And they may not be computable. Then for every data point, you're going to find the distance of the data point from each of the clusters, or rather the centroids of the clusters, using this formula, which I just presented 2 slides ago, where this is the distance of the data point from the centroid of the cluster in the high dimensional space. So you actually find that it's computing the kernel between the point and every data point within the cluster, but you're also computing all pairwise kernels within the cluster. It's an expensive formula to compute. But using this formula, you can figure out the distance of the data point from the virtual centroids for each of the clusters. And then put the data point in the cluster of the closest centroid. And so now you have your new clusters. And then when all the data points are clustered, in your standard k-means, you'd recompute the centroids. Here, we are not actually going to do this. So this step 4 is not done in kernel k-means. We're just going to be iterating steps 2 and 3 till the total distance is converges, right? So let me actually see if I can pull up this fourth poll. Can you see the poll? Fifteen seconds, guys. Okay, ending the poll. Here's what the results look like. And so let's go back. Can you tell me which statements are true? Kernel methods transform the data linearly into a high dimensional space, true or false? So why is it false? Anybody? The kernel function method transforms the data into it's non-linear. So the second statement, this is true, correct? Kernel methods transform the data non-linearly into a higher dimensional space. And so it's not linear. What about this third statement? So the second statement is true, correct? Now what about the third one? Euclidean distance-based clustering in the kernel space can discover non-convex clusters in the original data. True or false? Also true, right? Okay, what about the fourth one? The computational cost of computing the Euclidean distance depends on the dimensionality of the kernel space. Obviously not, right? You can compute the distance very cheaply, even though you're going into an infinite dimensional space. And let's check if this is true, right? So it's correct. Only the second and third statements are true. Very nice. And so here we have it, right? What we've seen so far is that clustering, first, k-means clustering is an instance of clustering. Clustering is basically a dictionary-based, it's an algebraic technique, which is based on dictionaries rather than bases. You're storing dictionaries as representative entries and expressing every data vector as a linear combination of the dictionary entries. Now, when the distance, the dictionary can be optimized to minimize the total error. And when the error we choose is an L2 divergence, you get the k-means algorithm. And the k-means algorithm is really easy to compute, but it only gets convex clusters. If you want non-convex clusters, you have to transform the data into high-dimensional spaces and then perform, Euclidean k-means there. But then now we are faced with the challenge of computing distances in this high-dimensional space. We avoid that problem by actually computing the distance in the low-dimensional space itself. And in this, we are aided by the use of kernel functions, which compute inner products in the high-dimensional space as some function in the low-dimensional space. And so you can compute this inner product without actually going to the high-dimensional space. Once you can do this, then you can compute the distance between data points in the high-dimensional space without actually going into the high dimensional space, without even knowing what that space is. And once you do that, you can perform Euclidean k-means in that high dimensional space without ever going there. And now you can get clusters which would be convex in the high dimensional space. But because the transformation is nonlinear in the low dimensional space, those clusters need not be convex, right? So there are some assumptions in all of this. Firstly, that the dimensionality of the kernel space, which is the high dimensional space, is more than the number of clusters. Yeah, yes, Abhishek?
So is the cluster the kernel function that we choose is some form of approximation of distance in the high dimension space?
The kernel function is an inner product in the high dimensional space. We
So
derive
it best approximates the distance of those high dimension points from its corresponding centroid, is it, in the high dimension space?
No, the kernel function kx1, x2 is literally just this guy, right? It is computing the inner product in this high dimensional space. That's it. The distance itself is derived by using these inner products in the high dimensional space.
Okay.
That answer your question?
Yeah, I think I have to just sit with this for some time. I mean, I'm just trying to wrap my head around how, like, the functions that you showed, like 4 functions that you showed, which were kernel functions, like how could they directly
They
compute
compute inner
inner
products in
products?
the high dimensional space, and you can
Okay,
you can sort of work that out, right?
okay, okay,
So now, and so what it turns out is that if you go to the right spaces, then your different clusters should end up lying along different directions, cardinal directions in the high dimensional space. Now, how many clusters do you need? You can define a kernel correlation matrix, which is, you can compute a giant matrix between where the ijth entry is simply the kernel computed between the ith and the jth training data. You can perform eigendecomposition of this kernel matrix, and you can see how many dominant eigenvalues you have. And that tells you how many dominant directions there are in the high dimensional space. And that is the optimal number of clusters in some sense. And there's some math behind this. So kernel methods are just one way of coming up with non-convex clusters. There are other methods. Spectral methods try to find principal subspaces in the high dimensional space. And clustering is performed on the principal subspaces, so things like normalized spectral clustering. And this involves finding eigenvectors and eigenvalues of the kernel matrix, but fortunately, all of this is provably analogous to just the kernel k-means that we just saw. So it's more about efficiency than concept. There are also other kinds of clustering methods. The clustering that we just saw is entirely based on adjacency of data points to one another. But you can have trend-based clustering. So here, for example, look at the data over here. If I try to find clusters, then I'm going to get, I can't really guarantee what the clusters will be, right? But if I could somehow fit this octagon, which is a piecewise linear approximation to a circle, and then cluster data points based on which of these line segments they are closest to, then I would discover that the data lie approximately in a circle. Or here, for example, if I have data which have this scatter, if I just ran Euclidean clustering using any technique, I'm going to end up with 4 clusters. But in reality, there are only 2 because there are 2 lines, right? And so you have clustering techniques which instead of just looking at the raw data points, they find a regression representing each cluster and associate each point to the cluster with the best regression. So this is related to kernel methods. And there are various other such techniques. So many variants. And of course, clustering has many, many applications. Most important is the choice of features. But the key idea is that it identifies latent structure and the distribution of the data. and simultaneously provides an L2 sense optimal quantized representation of the data. So these are things that we're actually going to build on in the next class. So I'm done here. Do we have any questions? Any questions? No. Okay. In that case, I'll stop sharing. And thank you all very much for being in class.
Thank you, Professor.